Hello, we are Team ME60. My name is Shane Back. My fellow partners are Natalie Connors and Cristiano da Silva. We were tasked with building a device to measure the coefficients of friction between cartilage and different materials in sliding, and our faculty advisor and sponsor is Dr. David Pierce. This was our problem statement. It was to design, build, and test a device to measure the static and kinetic coefficients of friction as a function of time between articular cartilage and other materials in sliding. What is articular cartilage? It's a bearing surface in synovial joints. It's free moving, such as your knee, hip, and elbow. It can be seen right here in the diagram. The purpose was to identify effectiveness of treatments to heal microcracks in cartilage. Dr. Pierce is doing an experiment where he is trying to see if you take a microcracked piece of articular cartilage and put it in thiolated hyaluronic acid, if it will have the same coefficient of friction as a piece of healthy cartilage. And our deliverables were a device, a user manual, a data processing script, and preliminary testing results.
To begin, this video shows our entire system running and collecting data live. We'll talk about the design, governing equations, and data processing in more detail later in the presentation, and we'll use this video to give context to those future discussions. Currently, there are small aluminum samples that are being used as our test specimens, which the lab will replace with cartilage for their full testing. Another thing to note is that the rotation of the system is driven by a motor.
On the left, we have our SOLIDWORKS rendering for our final design, and on the right, we have our real-life model. As you can see, the real-life model came out exactly as we had hoped.
Our final design consists of T-slotted framing for the supports. On the bottom, we have our DC motor that drives a shaft that rotates a sample dish. In between the two parts, we have a torque cell to measure the frictional force due to the loaded sample. The upper part of our design consists of two axially locked shafts with a load cell placed in between to calculate the load with respect to time, and up above that is a loading dish to allow us to select set weights for testing. In the dish where friction occurs, we mount a small square piece of cartilage to the base of the shaft. Here's an example of what a cartilage sample looks like on its side. Below that, on the sample dish, we have a large, flatter piece of cartilage that is lubricated in a PVS bath. These pieces of cartilage are slid against each other in a radial motion to collect our data.
Our device can be thought of as a record player with a fixed sample acting as the pin and a rotating sample sliding beneath it as the record. We'll now take a closer look at the forces at play between the samples of cartilage to determine our governing equation for the coefficient of friction. This free body diagram shows the applied force and the equal and opposite normal force. A torque is created from the motor since the system is rotating. Since the fixed sample is offset from the center of rotation a certain distance, the effective radius, the friction force creates a torque in the direction opposite the motor. We know from the definition of friction that the friction force is equal to the coefficient of friction multiplied by the normal force. We also know that the torque due to friction is equal to the friction force multiplied by the effective radius, which again is the distance the fixed sample is offset from the center of rotation. Combining these two equations, we determined our governing equation for the coefficient of friction, where we measure our torque due to friction with our torque sensor, the normal force with our load cell, and we manually measure the effective radius with a set of calipers. Here is a closer look at our data acquisition done in LabVIEW. On the left, the data is being collected from both the torque sensor and load cell at a rate of 1 kHz. On the right, our block diagram splits the incoming signals and filters out the noisy high frequencies. The data automatically saves to a file that is ready to be processed in MATLAB. We use MATLAB to process our data. The script prompts the user to enter the effective radius that was measured with calipers. They are then asked to enter in the file name of the raw data that was saved from LabVIEW. A graph is quickly generated that displays the coefficient of friction as a function of time. Right at the beginning of this video, we start collecting data. You can see the jump in values when we start the motor. So again, the small aluminum samples will be replaced with cartilage from the lab. And to put it all back into context, the team is researching the development of microcracks in cartilage for people with osteoarthritis. The new device is going to quantify the damage to the cartilage, where changes in the coefficient of friction, measured by the device, will indicate potential treatment targets. We're excited to pass our device along to Dr. Pierce and his team to continue their research here at UConn School of Engineering. Thank you.